Okay, so we want to be able to record and do calculations on not just integers but decimal values as well. And to do that, we need to introduce a few new concepts. The first is that this individual number is going to be decomposed into a few different parts, as you see here. A sign, the mantissa, which is the coefficient out in front, and the exponent. And there's going to be a special rule associated with that, which is that the mantissa is only allowed to have values between 1 over b and 1. The reason for that is to make sure that there's only one way in which the number is being encoded. And so for base 10, the rule is that it has to be within 1/10 and 1. And to give you an example of that, say we had a number 156.78. We would need to rewrite that in terms of 0.15678 times 10 to the 3. So now that its mantissa follows the rule that it's in between 1/10 and 1. So we're not allowed to write it this way or write it this way. That way there's only one way in which we can write this. In base 2, then we're restricted to 0.5 or 1/2 and 1 for the mantissa values. Okay, so let's look now at how we can use this floating point system to represent numbers. So basically we're going to be trying to convert an 8-bit floating point number to base 10. So we have 3 different sections. We have the mantissa, which is right here, the signed exponent, which is right here, and the sign of the number. So we have kind of 3 different sections, and this section right here has both the sign and the magnitude of the exponent right here. And so what we'll do here is, first, this is the binary number. Let me remind you with this table here on the right what its values stand for. So here would be 2, 1, 0.5, 0.25, 0.125, and 0.0625. Okay. And note that our number has a 0 right here, which means that it's a positive number. And so we see that its exponent is negative. So e negative, and it's going to be 2 plus 1 equals -3. And since it's mantissa, we have zeros out here and a 1 right here, so it's just 1 times 0.5 is 0.5. Okay, and so then we use the formula that we had at the top to represent this in base 10. So MBE, so 0.5 times our base of 2 to the -3. And if you calculate what that is, that equals 0.0625. So this is the base 10 representation of this number. Note that if you want to do this for other problems that have different floating point systems, the numbers that you need are the number of bits that are used for the mantissa. Like in this case, it was just 4. The number of bits that are for the signed exponent, in this case, is 3, and the number of bits for a signed number, which is 1. So let's look at a few more examples, and you want to be able to convert these to base 10. So we had already said that a mantissa right here is going to give us 0.5. So this is our mantissa is 0.5 for this first problem, times a 2 to the minus 3, because we have 1 right here, plus 2 to the 1 minus 3. And then we have a positive number. So this is really this is actually the same problem that we already did it before. And then in this next example, we're having the same mantissa. Everything else is the same except one additional positive value right here in the mantissa. And this value, as you remember from the last one, is 0.0625. So we add that to the mantissa, and that would give us a value of 0.0703. And using that same sort of arithmetic, I encourage you to complete these next two values. You can pause the recording to do that. And if you've done that already, we can look at the values you'd expect to get. You'd see that for this third problem, we had, we moved that bit from this one to this one, which brought us our mantissa up to 0.625. The exponent was the same. And then finally, on this last problem, we had an exponent that was positive. So that was 2 to the 3. This stands for 2 to the 3. And then we had the maximal possible mantissa, which was 0.9375. And so you multiply all those together, and you get 7.5. So one of the questions you might ask yourself looking at this is, well, in these examples, why did we have all ones in this column right here? And that comes to the rules that we had on the previous slide right here, where the base had to be between, in a base 2 system, it has to be between 0.5 and 1. So that's a minimum. It's a minimum that can be recorded. Okay, so what we've looked at so far shows us how to represent numbers in these base 10 or base 2 systems. And so now let's look at how that affects the error. So one of the things that we see is that in these numbering systems, only certain values could be represented, and the others got skipped along the way. And so what happens is, if you on the computer you enter a number like 0.0703, in this system it gets chopped down to the next lowest value that the computer can actually store, because it can't store this number of 0.07. And so that leads to a round-off error, where the round-off error is the difference between the actual value right here and the number that it gets chopped down to of 0.0625. And so the round-off error in this case is 0.0075. If you want to compute the relative round-off error, that might also be useful. You look at the difference between these divided by the smaller number right here. And so that's a relative round-off error of 0.12, or 12%. You always divide by the smaller number. So this shows that when you can only represent the numbers shown here as the crosses, that leads to quite a bit of error in the computations that you might have. So the maximum round-off error really has to do with the magnitude of the numbers and the proportion of that with the spacing between the numbers. So you can see that, like as in the last example, the spacing between these two items kind of dictates how much round-off error you would have. And so the relative round-off error you can get in this system is given by the ratio between the distance between marks and the smaller number, like this. And so you can kind of subtract that and divide, and you see that the maximal round-off error that you get is 0.125 when making this comparison. And There's one way of computing the round-off error that you could achieve. One of the important results is that there's something called the machine epsilon, such as this, and that machine epsilon is the kind of upper bound or theoretical limit on the amount of round-off error. And just simply by looking at some of the basic properties of a numbering system, such as its base and t, the number of bits representing mantissa, you can compute the round-off error, or I'm sorry, the machine epsilon for that system, and see that you can, in this case, you could get up to 12.5% error in calculations. So here are just like some other kind of examples of where you might get round-off error. As we see, this round-off error comes from not representing numbers exactly in the computer, and so it usually becomes an issue when there are a limited number of significant digits used in floating point. The trade-offs here is that if you save more and more numbers, that requires more and more memory in the computer, and so there's a trade-off between the memory that a computer has and the round-off error that results in computations. One issue where you encounter a lot of round-off error is when you're adding numbers of very different magnitudes. So as you can see here, you can see quite a spread between these, and what happens is it will chop. These are exaggerated examples, but it will chop this down so that it is adding this as if it was 0 and give an incorrect answer, as you see here. Or if you're subtracting numbers with very similar magnitudes, you should watch out for round-off errors in your computations, such as this example right here, that it's artificially, the result makes sense, but it's artificially adding more significant digits, and there are going to be error in these artificially added digits, and so that's going to lead to more problems in the end. So those were some of the more theoretical aspects of round-off error and how that affects your computing. So that will hopefully help you pay attention to what data types you use to store your variables in. So it's good to know that NumPy in Python uses double precision, or 64 bits by default. So that's a lot more memory than was in our examples that we had in the previous slides. So it'll use 1 for the sign, 11 bits for the exponent, and 52 bits for the mantissa. The reason why it's using so many bits is that it wants to store these values quite accurately. It's also important to know that different data types use different numbers of bits. So you want to be able to check your data type in the Spider's Variable Explorer. And that there are some cases where you want to decrease the precision, such as when you're using a computer that has very limited memory, or you want the computing to go very fast. So let's just quickly go back to Spider and take a look at some of these. So for example, if I say I equals 1, and you look in the Variable Explorer, it's showing that it's an integer, right? If I say np or a equals np array dot 1, 2, 3.1, something like that, we can see that it's an array of floating point numbers that are 64 bits. So that's telling us how much memory is being used to save that number. And you can also do like a.dtype, which will tell you that the data type for that number. There are also, so you can have integers, we said. You can have these floating point numbers. You could also have, I'm just making up a list here. So G is a list right here, whereas H equals 1 is a string. So it's important to be paying attention to the data types in the Variable Explorer, because that can have a big impact on your computation. So hopefully that was useful to you, and I'll see you next time.